Alrighty, well, welcome to either week 8, lecture 1 if you're in 230, or week 2, lecture 1 for 232. And so today I'm going to talk about a few ideas that are addressed on some of the problems in section 15.2, and then we'll get into section 15.4 and a little bit of 15.6, which for 230 people, remember you have your second midterm this Saturday through the following Wednesday. So I believe that's the 6th through the 10th of July. Yep. And that's going to cover through what we talk about tomorrow through the end of 15.6. So anyway, let's take a look. And so I wanted to talk about first some shortcuts for certain double integrals. Now that you've had a chance to work out some double integrals last week, I'll show you some shortcuts. So let's just do a quick review of some of the interpretations of what these various integrals mean. So yeah, when you learned about integrals in Calc 1, you probably thought about it as area under a curve. So the single integral a to b f of x dx gives you the signed area, of course, under the curve y equals f of x and the x-axis. So if you have area that's below the x-axis, that counts negative. Above the axis counts positive, so that's why we say signed. And so that's analogous to our first interpretation of what a double integral represents. So last Monday when Dom was introducing the idea of double integrals, the idea was that when you do the double integral of f of x, y, it gives you the signed volume under the surface z equals f of x, y, and above the region D in the xy plane. So it's just the same idea as in Calc 1, except scaled up one dimension. So instead of a curve y equals f of x, you have a surface z equals f of x, y. And instead of talking about area under a curve, you're talking about volume under a surface. Okay, and so that's just a quick review. But let's talk about another thing that you can do with integrals. So in Calc 1, if you were to integrate the boring constant function 1, so integral a to b of 1, you could write that as just integral a to b of just plain old dx. So you don't have to write the 1, right? You could think about that as multiplication, even though it's really not multiplication, but for all intents and purposes, you can think of it as multiplication. So 1 dx obviously is equal to dx. And so when you do the integral from a to b of dx, you plug in a and b into the antiderivative of 1, which is x, and so you of course get b minus a, which you can recognize b minus a as the length of the interval from a to b over which we were doing our integration. And so we have this similar idea in double integrals, that if you do the double integral of the boring constant function 1, and you could write that as double integral of 1 dA or just double integral dA, that gives you the area of the region D. And so that's something we're going to continue to see later today, as well as later on in the course, that essentially that's a property of integration in general, that when you integrate the boring constant function 1, you get the appropriate notion of size of the region of integration. And for triple integrals, that'll be something involving volume. For line integrals, it'll be the length of a curve. For surface integrals, it'll be surface area. That basically, the integral of 1 is the size of the region of integration, and size being measured as appropriate for the type of object we're talking about. And so a combination of what we just said with volume under a surface as well as area of a region, sometimes you can recognize known volumes or known areas and use that as sort of a shortcut for calculating these integrals. So I'll show you an example in a couple minutes, but we'll talk about odd symmetry first before we do a concrete example. So odd symmetry, remember in Calc 1, you probably talked about the idea that if you have an odd function, so what does it mean for f of x to be odd? Well, it means that f of minus x is minus f of x. So not all functions have this property that putting a minus on the input is the same as multiplying the output by -1. Even functions doing f of minus x actually does nothing. It gives you the same thing as f of x. But for odd functions, this minus sign can be pulled outside. And so if you integrate an odd function on a symmetric interval about 0, so symmetric about 0 means your interval is going to be something like minus a to a of f of x dx, that gives you 0. And so the picture is that, well, this odd symmetry, if your function obeys this, that tells you that y equals f of x is symmetric through the origin, is what it's usually called. So for example, if I have a point here and I draw the line to the origin and I keep going the same distance, I get another point there. Whereas like this point here, if I go through the origin, I get this point over here. Maybe my picture isn't perfectly symmetric, but you get the idea. And so here it's pretty clear why this integrates out to 0, because if I have this symmetry, this area here is the same as this area over here. And remember, we're doing signed areas where the area below the axis counts negative, the area above the axis counts positive, and so they cancel each other out. And so you would say that there's, no net area. If you're thinking of net area as taking this signed area idea, where area below the axis counts negative, area above counts positive, they cancel each other out. Okay, so that was something you had in Calc 1. And so how is this idea going to help us now? So for double integrals for functions f of x, y, we have two different notions of oddness. So the first, though, we could say is odd with respect to the variable x, which if you think about it, it just makes perfect sense. So, with odd, we're doing the input multiplied by -1, but now that we have two variables for our input, we could talk about being odd with respect to either one. And so let's start off with being odd with respect to x. So that means that f of minus x comma y is minus f of xy. So if that's the case, and if you think back to Calc 1, there's also something special about the interval that we were integrating. We weren't just doing a to b, we were doing something from minus a to a. We had to have this symmetry in the interval as well as the symmetry in the function. And so anyway, what we need for an odd function with respect to x is going to be symmetry over the y-axis. So if I draw, let's say this triangle here is my region D, then I have symmetry over the y-axis. This might seem backwards, right? Some of you might be thinking, is that a typo? This is x symmetry. Why are we going over the y-axis? Well, it has to do with the fact that you would say that D is invariant under the transformation x goes to minus x. So when you replace x to minus x, that's reflecting over the y-axis. So essentially what you're saying is that the behavior of f is opposite when you switch x to minus x, and the region is the same when you switch x to minus x. And so those are the two ingredients we need together in order for this to tell us that the double integral is 0 over this type of region for this type of function. And so intuitively, how can we explain this? Well, so one way you could think about this is, remember the idea of a double integral is being the limit of a double Riemann sum. And so what's a Riemann sum? You're basically adding up a bunch of stuff. You're adding up the values of f times the area of some small sub-rectangle, let's say. So whatever I'm getting to contribute to the double integral for this point is going to get exactly canceled out by this point over here. If f of minus, because this point here would be x comma y, this point over here is minus xy. So because f of minus xy is minus f of xy, those 2 points are sort of canceling each other out when you're doing your double Riemann sum. And the fact that this region is symmetric over the y-axis tells you that every point on the right-hand side has a partner over on the left-hand side at which f is counting exactly opposite. And so therefore, in the double Riemann sum, you get this cancellation. When you take the limit, you're going to get 0. So that's one way you could think about it. That, yeah, you have minus, that's the idea, that minus f of minus, you can move this minus sign over here, of course, whatever. You get the opposite contribution. The other way you could think about this, too, is if you were to set it up as a dx dy double integral. If your region has symmetry over the y-axis, when you go to think about the left and right curves, let's say that the right curve has equation x equals g of y. Well, the symmetry in the region tells us that the left curve is then going to be x equals minus g of y. So when you go to set this up as a dx dy double integral, the inside integration is exactly the type of thing that in Calc 1, since we're doing an x integration odd with respect to x, minus g of y to g of y, that would be 0. And so then the integral from c to d of 0 is 0. So you can intuitively think about it as far as like this sort of cancellation when you're adding up all the values of f. But then additionally, you could see it as following directly from the Calc 1 idea that when you do odd function symmetric interval, you get 0 as the inside dx integration for this, and you end up getting 0. Okay, and then obviously you've probably figured out that what's so special about x? What if I have a function that's odd with respect to y? Is that also going to have a similar type of property? And the answer is yes. If I have a region that's symmetric over the x-axis and a function that's odd with respect to y, then yes, the double integral of such a function over such a region will also work out to be 0. So for symmetric over the x-axis, that's going to look something like this for your region D. And odd with respect to y, you could figure out what that means just by thinking about what it was with x. Okay, so anyway, a lot of this seems tricky. So let's do the double integral over d of x plus 3x squared y plus 4 minus x squared minus y squared dA, where d is the disk x squared plus y squared less than or equal to 4. And so this symmetry idea, you don't have to use it. It's sort of optional, but let's pretend we don't know it for right now. How would we set something like this up? So as soon as you see this disk, this region of integration is a disk of radius 2 centered at the origin, that's a big hint that I want to use polar coordinates, right? Anytime your region involves a disk, you're going to want to use polar coordinates. So the long way of calculating this out would be to switch to polar. So this polar bounds for this disk is going to be 0 to 2, 0 to 2 pi for r and theta respectively. X is r cosine theta. 3x squared y is plus 3r cubed cosine squared theta sine theta. 4 is just 4. And then this would be the square root of 4 minus r squared. And then don't forget your additional factor of r that shows up in dA for polar coordinates. And then you'd go from there. So nothing too terribly bad. Make sure you're able to finish that out. But as it turns out, I've picked this example to be something that you don't actually have to do any integration for at all. So, okay. Altogether, this integrand is not odd with respect to x. It's not odd with respect to y. It's not an area that we recognize. And it's not a volume that we recognize. But if we split it up term by term, then it turns out that we do have different ingredients on the various pieces that do allow us to use some shortcuts. So again, integration, just like in Calc 1, is well behaved over addition, subtraction, and constant multiplication. So the shortcut way would be to realize that, okay, yeah, this is the double integral of x plus the double integral of 3x squared y plus the double integral of 4 plus the double integral of square root of 4 minus x squared minus y squared. And so it turns out piece by piece, we have some of the shortcuts that I talked about just a few minutes ago. Okay. So the first thing to notice about this region is that it's an entire disk, so it's symmetric over the x-axis, which means that every point here has another partner point down there. And so symmetry over the x-axis, we're on the lookout for things that are odd with respect to y. So in my term 3x squared y, if I change y to minus y, 3x squared minus y is pretty clearly minus 3x squared y. That's what it means to be odd with respect to y. And so the symmetry of the function, the odd symmetry of the function, and the symmetry of the region over the x-axis tells me that that integrates to 0. And so if you hadn't seen that, you would have gotten it here, because what's the antiderivative of cosine squared sine? You could do u equals cosine theta and gotten the antiderivative minus cosine cubed over 3, which when you plug in 0, 2 pi and subtract would, of course, give you 0. So if you don't see these symmetry tricks when you are doing something like this, like where it's a disk, if you don't see it, it's going to manifest itself later in the theta integration in terms of you getting something that cancels out once you get the antiderivative, plug in, and subtract. So anyway, it's not the end of the world if you don't see the shortcut. You'll still, of course, get the same answer. But yeah, we have odd with respect to y, symmetry over x-axis, so that term is 0. Okay, well, what else do we have going on here? Well, our disk is symmetric over the y-axis as well, right? And x is odd with respect to x, right? Changing x to minus x is the same as multiplying the whole thing by -1. So odd with respect to x, symmetric over the y-axis tells me that that integrates to 0 as well. Okay, so we've got 0 plus double integral of 4 plus double integral of square root 4 minus x squared minus y squared. Okay, so this double integral of 4, I know, is 4 times the area of D. And so that's true in general. Anytime you're doing the double integral of a constant, your answer is that constant times the area of the region of integration. That doesn't always help. If you have some weird shape D, you might not know the area. This really only is a good idea, or I mean, it's only a useful idea when you know the area of region D. And well, guess what? We do. It's just a disk. So this is 4 plus pi 2 squared, well, sorry, 4 times, getting a little ahead of myself, pi 2 squared, that's that. And so I'm running out of room a little bit. Let's see if we can finish this off. This last term, square root 4 minus x squared minus y squared, it turns out that we know that double integral as well because it represents a known volume. So later on, I guess next week when we start practicing with something called cylindrical and spherical coordinates, you're going to get a lot more comfortable with these types of equations. But let's just interpret what this double integral means according to the very first slide from today, as far as volume under a surface. This is the volume under z equals square root 4 minus x squared minus y squared, and above the xy plane. Well, what is z equals square root 4 minus x squared minus y squared? That's the top half of the sphere x squared plus y squared plus z squared equals 4, right? Solve for z, take the positive square root, which means you're taking the top half. And yeah, that's what we're dealing with there. And it tells us then that the shadow, this D that we're dealing, the region above which we're doing, that's the disk x squared plus y squared less than or equal to 4. So, you know, just because you're doing the double integral of this square root doesn't mean you're getting this entire half ball volume. But we are, because this region of integration D, we were already told a while ago, is this disk of radius 4. And so basically, I then can recognize this is half the volume of the sphere of radius 2, right? Because our sphere has radius 2 over there. And there we go. So these are some tricks that you can use. The first few homework problems for this week are using ideas like this. So you're going to have to draw your region anyway to figure out the bounds. Remember, so anytime you go to draw a region, maybe think about, okay, do I have x-axis symmetry? Do I have y-axis symmetry? Is there symmetry in my integrand? If not in the entire integrand, can I break it up into different terms and observe certain shortcuts term by term? Those are some things you can think about. And so like I said, the first few homework questions, you'll get some practice with ideas like this. So integral of constants, you want to think of as that constant times the area. And otherwise, just keep in mind double integral of f of xy is the volume under z equals f of xy. Okay, and so then 15.4, the first section, new section we're going to get into today. It's basically answering the question, what else could double integrals calculate? We saw sometimes it's area if you do a boring integrand, or otherwise you want to think of it as volume under a surface. Okay, well, instead of thinking about it like that, here's another example. So let's suppose we have a lamina. So a lamina is just a fancy way of saying a thin, I guess it actually means layer, probably. But in this course, when we say the word lamina, we're thinking of, let's say, a thin plate that's so thin that we treat it like it's a two-dimensional object. And so let's say we have a thin lamina, and some parts of it are heavier than other parts of it. So, you know, we could think about a piece of paper where you have some like heavy ink that's on certain parts of it and light ink on other parts. You know, maybe you're making ink out of gold or lead or something really heavy, but you have something where you have mass distributed along a two-dimensional object non-uniformly. And so in order to describe the fact that certain parts of this lamina are more dense or less dense than other parts, we're going to capture that using something called a density function. And so later on next week, we'll use this same Greek letter, rho, R-H-O is how you spell it in English, but rho, I guess using it to represent density is sort of coming from the historical conventions of gas dynamics, as far as I know. But anyway, maybe you see this in physics, but rho often stands for density, and that's what we'll let it do right here. So this function rho of xy is going to tell us the density at the point xy. And so for now, let's think about mass density. So the units of this on our two-dimensional object is kilograms per square meter, let's say. And yeah, that's the idea. And so in general, with constant density, let's say rho is just equal to rho naught, you guys probably know from other courses that mass would just be density times area. But the idea is that for this lambda that we're thinking of here, you know, the density isn't constant. And so what you could do is you could set up a double Riemann sum and say, okay, well, the mass is whatever it is here plus whatever the mass is here. And the idea is that these little subrectangles are so small that you can treat density as approximately constant and then add this up, take the limit, and it turns out that, yeah, you end up getting the double integral. So when density varies, oh, what is going on here? When you have variable density, you do the double integral of that to get the total mass. And so you could think about the units as following. So we already said you want to think of rho of xy as units kilograms per meter squared. And you could think of this dA as having units of meter squared, so that when you do this double integral, you're sort of multiplying these units together to get kilograms. So you want to think of dA as having units of area. If you think about where it came from, remember we were doing these double Riemann sums where we were doing like rho of xi, j, yi, j star times delta A, where delta A literally was the area of some subrectangle. So when you take the limit, think of dA as having units meters squared. So a lot of times these differentials in your integrals, you can sometimes get away of thinking about them as just sort of optional pieces of notation, but I think we really should think of them as being there and being an important part of the notation so that dA has units of area. That's why we use dA as the label. So anyway, you do the double integral of density on a two-dimensional object, you get the total mass of that two-dimensional object. And so you can have other densities as well. So in physics course, probably physics 212, you probably talked about charged plates. And so if you have charge on some kind of plate that's non-uniformly distributed, you have some charge density. I just picked sigma, lowercase sigma of xy, to be your charge density. And so let's say that the units for that are coulombs, capital C, coulombs per square meter. Then when you do the double integral of charge density, you get the total charge on the plate. Another way you could think about it, sort of a very easy to understand real world application, is population density. So think of State College. You go north of campus, well, I guess you go north of the stadium, there's nothing out there except farm, right? There's nobody who lives there. Whereas if you go, south of this, or a little bit west of the stadium towards the East Hall dorms, there's lots of people that live there. So you could have a density function giving population density. So maybe how many people per square mile live near a point. And so, when you go up to the farm north of campus, there's nobody living there. But if you go near one of the dorms, you have a certain density of people. If you go to some of the houses south of campus where they're only 2 or 3 floors high, you have a different population density. So you have people spread out non-uniformly in terms of where they live. And so if rho of xy is your population density in people per square mile, and you do the double integral of population density, you get the total number of people, if I could spell. Or the total population is what you would call it. So anyway, I don't think there's really any examples we have to do. You'll get some practice on the homework, but you're not always going to want to think about double integral as area, or remember, area is for boring situation, boring constant integrand, volume under a surface, but you could also think about it as the total whatever when you're integrating some kind of density function. So whether that's mass, charge, people, who knows? And so, okay, the next thing we could talk about is something called moments. So let's go back to thinking about our thin metal plate with variable density. Maybe it's made out of aluminum in some places, lead in other places. And so you have some parts of your plate are heavier than other parts of the plate. And so we could define the moments about either the y or x axis as the following. So again, you might think that I made a typo here, but I did not. The moment about the y-axis involves the distance to the y-axis, which is actually x. So yeah, it's not a typo that m sub y involves x times this density. And similarly, moment about the x-axis involves y times our density. So anyway, those are our moments. And so why are these moments useful? It turns out that they're useful for finding something called the center of mass. So center of mass is very important as far as physics goes. Often, if you have, say, 2 point masses, and you're trying to figure out how they interact with other objects, it turns out that as long as you stay, outside of these two objects, or I guess no matter what, you have these 2 point masses, the equations of motion are equivalent to treating it as a single point mass at the center of mass. So the single point mass you're pretending would have the total mass of the two put together, plus, and then it would be located at that point mass. And so effectively, that's how those 2 point masses would affect other things. And it makes sense, and you can also do that for continuous mass distributions as well. So if you have, essentially, this is in 3D, but if we were in 2D, and I want to know how this book here was interacting gravitationally with other objects in this room, well, it turns out that instead of having, something complicated like the density of paper, the density of ink, the density of the cardboard cover, the density of the glue and the binding, all that fun stuff. Well, I could just take the total mass of this book and then figure out where the center of mass is and treat it as a point mass located at its center of mass. I think this has to do with the reason why Pluto got booted off of the list of planets. I think the issue with Pluto is that the center of mass of it and its moon is outside of Pluto. I guess in physics, the word center of mass is often called the barycenter. So anyway, idea of center of mass is, I'm sure you guys have heard about it before. You don't really need me to convince you that it's something that's done and discussed. And so anyway, it turns out that the center of mass for this lamina D that we're talking about would be the point at which you could balance it. So if I have my thin metal plate and I want to balance my thin metal plate at some point, I would be able to do that at this x bar comma y bar. And it turns out that the formula for that is the x coordinate of the center of mass is the moment about the y-axis divided by the mass. And so you have double integral. Now you just use the definitions we've used before, that the y-axis moment is that, and the mass is that. And so I only bring this up because a lot of people, when you look in the book, you'll see this. We're not going to ask you about moments in this course. We will just ask you about mass and center of mass. So you can forget about that slightly confusing idea that the x bar involves the y-axis moment, which involves the integral of x times density. You could just forget about that intermediate step if you choose. But anyway, the way I remember it is, yeah, x bar has the extra x, y bar has the extra y. That's what's important. And so just go ahead and do those. Again, the problems for that are pretty straightforward, just setting up and practicing with more double integrals. So that's another thing double integrals are used for. Mass, center of mass, in addition to volume under a surface. And so that's all we're going to worry about for the test and exam, the exam and quizzes. But just for fun, I thought I'd list a few more ideas that you can use double integrals to calculate that you might have heard about. So in physics, you might have heard about things called the moment of inertia, which is important in figuring out, well, the one that comes to mind would be the moment of inertia about the origin would be what you need to determine. What am I trying to think here? I think it comes up when you start talking about rotational kinetic energy and angular momentum and things like that. Or if you were trying to derive the equations of motion of an object that could rotate, then yeah, you would need to know the moment of inertia about the thing that it can rotate. So anyway, this comes up in a lot of physical applications. And so whereas our first moments that we were talking about in the context of center of mass involved x and y times our density function, it turns out that the idea of moments of inertia, you add in factors, or you put in factors of x squared or y squared, or if you're talking about moment of inertia about the origin, you do x squared plus y squared. So these are just more examples of double integrals where we have our density function, rho of xy, times various other things, and they do that. So I guess, yeah, in Physics 211, I'm sure you guys have formulas for moments of inertia for different objects, and you're asked to do things with them. The way you figure out the moment of inertia for an object in general, you would have to do some kind of double integral like this. So if you have something really complicated where it's heavier in certain places, lighter in other places, you'd really need to use this type of multiple integral to get those moments of inertia. So anyway, that's important. And then the other fun application that I want to talk about is probability. So some of you might be wondering, I'm a stat major, why do I have to take this course? It seems like we're talking an awful lot about physics and things like that. Well, if you're a stat major, the reason why you're taking this course is because multiple integrals are extremely important for talking about multiple random variables. So to put this into language you might see in your probability courses, so if you have random variables x and y, and you have a joint density function f of xy, then the probability that x and y are in some set D is the double integral over D of this joint density function. And so for probability densities, you want to think about this density function as being non-negative. So it's just like mass density, so mass can't be negative. And the idea is that the probability that x and y take any possible value so that they live in R2 is 100%, which means that you could think about this as the total mass of a probability density is 1. That's sort of what probability densities are. They're basically like mass densities, except the total mass is 1. And so that way, since f is non-negative, you'll never get a negative answer for the probability of something happening. So anyway, what's a concrete example of how this could turn up? So let x and y be the height and weight of adult people in the world, and then f of xy is the joint density function. So the way that this joint density function captures things is that, let's say I want to know the probability that if I pick someone random in the world, what's the probability that they're between 5 and 6 feet tall and between 170 and 190 pounds in weight. So the idea is that then you would do the double integral over that region, that rectangle of this joint density function. So you do the double integral from 5 to 6, of 170 to 190, of this joint density function. And so other things could be more complicated, like not every region you'd be dealing with here would be a rectangle. But I don't want to get into anything too tricky. We're not really going to do any word problems regarding this, but you might wonder, okay, you know, in probability class, you'll learn about the difference between independent random variables and random variables that aren't independent. So there are some situations where if you have two random variables that don't care about each other, really, in some sense, this joint density would actually separate as something in terms of x times something in terms of y, in which case, you know, you might be able to answer a lot of questions without really understanding double integrals in all that amount of depth. But a lot of random variables are not independent of each other. So for example, I'd like to argue that height and weight are not independent. I mean, obviously you can have tall, skinny people and short, fat people, but in general, I would say that the taller somebody is, odds are they're going to weigh a little bit more. So knowing someone's height doesn't really tell you their weight, but probability-wise, it does tell you something. So I think if you were to look at the probability joint density function for people's height and weight, it wouldn't be independent of each other. So anyway, this f of xy really would be a two-variable function that you can't understand in terms of the variables separately. So anyway, that's what a probability density function would do for you. And just other fun ideas, things like expected value or average or first moment. It's kind of like that first moment that we were talking about as far as mass density goes. So if you want to know the average weight of, or height, I forget which variable I used for which, I guess x is height. So using the language of our previous example, the average height of everybody in the world, you would calculate it by doing the double integral over all of R2 of x times the joint density f of xy. If you wanted to know the variance, which is also a synonym for that, is second central moment, you would do the double integral of x minus the average, that quantity squared, times your joint density. And it turns out that you take the square root of the variance, you get something called standard deviation. So if you're in statistics, eventually you'll learn all about this stuff. And multiple integrals are what you're going to need to understand to deal with multiple continuous random variables at a time. So there's other fun stuff. I guess the third central moment would involve like a cube here. A fourth central moment would involve a fourth power. And those would be other features of your probability density function that you're talking about. So anyway, like I said, this moment of inertia and probability stuff, don't worry about for quizzes or tests. It's not even on the homework either. But just to show you that multiple integrals have a wide variety of uses. But anyway, let's kick it up a notch and start talking about triple integrals. So let's get crazy. So first of all, we have a solid region E. So for some reason, we'll use D to mean a region in R2, E to mean a region in R3. We'll just follow the conventions used by the textbook. So solid region E is in R3, and we have some function of three variables, f of x, y, z. So we're going to use this notation for the triple integral of f on the region E. So three integral symbols, region E, f of x, y, z, and then we're going to use the notation d capital V. Remember, we did dA for double integrals, so we'll use dV for triple integrals. So what does a triple integral do? Sometimes it's a volume. And so when is it a volume? It's a volume when the integrand is the boring constant function f equals 1. So this is an extension of our probably second slide from today, third slide, I think, that single integral of 1 is length of an interval. Double integral of 1 is area of a region. Well, triple integral of 1 is volume of a region. So that's one interpretation of a triple integral. And so just like how we used to think of dA as having units of area, you should think of dV as having units of volume, hence V. Okay, well, if that's what I get with a boring integrand, what do I get with an interesting integrand, f of x, y, z? So I think the biggest pitfall that I see with people keeping things straight in this part of the course is a lot of times people are going to think that triple integrals always represent volume. And I don't think you should think that, because it's true that it does in this boring integrand case. But if I have f of x, y, z, and I'm thinking of like this as, you know, I have some, that f is some length in some space, then I end up getting meters to the fourth is my units, which then that's sort of pretty tricky. So this I don't really want you to think about, but I just want to try to explain to you where this is coming from. So all we're doing here is extending the ideas that we've talked about before. That in Calc 1, you had an integral was the area under y equals f of x, right? That was what you did in Calc 1, that the graph of a function of one variable is a curve in 2D, whereas a graph of a function of two variables, so the graph of f of xy is the surface z equals f of xy in R3. So double integral f of xy is already a volume. So when we do the triple integral of f of x, y, z, and we want to attach some sort of area or volume interpretation to it, we got to go into 4 dimensions. So I'm going to do my best here and try and explain how you could visualize R4. So let's squish R3 into a plane. So this is kind of weird, this is kind of silly. And then I have my W axis coming out here. So you know, my X, Y, and Z axes are all squished down into this two-dimensional thing. So this is not a good picture. But if I want to think about the graph of f of x, y, z, it's the hypersurface. So this is a curve, this is a surface. W equals f of x, y, z is a hypersurface in R4. And so the triple integral over E, so E is some solid three-dimensional region that's now been squished into 2D. And now I have this like 4D volume going on. And so, I don't know. I think you need to be on drugs to understand 4 dimensions, and we shouldn't take drugs in math class, so I don't think this is how we're going to want to think about this stuff. But you could, if you could do this without drugs, that's fine. But one interpretation of triple integral is the 4D volume of W, 4D volume under, and yeah, I don't know what you want to call this other than 4D volume, but we've run out of dimensions. And so this isn't the best way to think about it. So instead, I think we should think about it in terms of density and mass. So maybe you were actually a little bit weirded out earlier today when we were talking about these lamina, the thin metal plates that are so thin we pretend that they're two-dimensional. Obviously, in our real physical universe, there's nothing that's actually two-dimensional. This piece of paper right here is not two-dimensional. It actually has a thickness. It's pretty thin, but if you zoom in, you'll see that paper is not 2D. It's in fact 3D, like everything else in our universe. Except I don't know what the hell electrons are. I don't know if anybody does, but let's just think normal stuff and not get too weird with it. But anyway, piece of paper is actually a three-dimensional object. And so in some sense, let's now think that we have a three-dimensional object, like maybe our body or this room or this book. Well, let's just think about this room, for example. So mass is distributed non-uniformly in this room. You got the air, which has, you know, it's not very dense, but there is mass in the air, right? Otherwise it would suffocate. It's not a vacuum in here. But then you have the density of paper, right, in this book. You have the density of cardboard on the book's cover. You have the density of metal on part of my laptop. You have the density of, I don't know if this is a real wood desk. Probably particle board, I don't know. But you have whatever that density is. You have these metal drawers. You have water that's in our bodies. You have bone that's in our bodies and whatever. So you have this density function, f of x, y, z, that gives us the density in kilograms per meter cubed at the point x, y, z. So let's say we have a solid object E. So this room is our solid object E. And f of x, y, z tells us how much mass is at the point x, y, z. Well, then the triple integral calculates the total mass in this room. So essentially, I don't think I'm going to write out what the idea is, but a triple integral, you can take a triple Riemann sum and take a limit. Essentially, that's what I would do if I wanted to figure out the volume in this room, right? I could take this room, chop it up into a bunch of little pieces. You know, if my piece consists of air, I have the density of air times the volume of that piece. I have, if it's a piece of this book, the density of the book times the volume of that piece. And you're just sort of sliced it all up, added it all up, and then taken a limit, and that's the triple integral that you would get. So this is what I really highly encourage you to be the interpretation of a triple integral. A lot of people think of it as a volume. Don't think about it as a volume. Think about it as a mass. It's equal to volume when you have a boring integrand, which in some sense, just think about this as being an object whose density is 1. For an object with density 1, which I guess if you're using certain units, that's the whole idea of water, right? That at standard atmospheric pressure and at standard temperatures and all that fun stuff, water is special in that the mass in grams is equal to the volume in cubic centimeters or milliliters. So yeah, water, mass, and volume are the same because the density is 1. But usually you want to think of a triple integral as not spitting out volume. A triple integral is spitting out mass. Integrand has mass density units, dV has volume units, and so you get kilograms as the units of your triple integral. Okay, so let's start talking about triple integrals then, how are we actually going to do them. So the first thing we did with double integrals last week was talk about double integrals over rectangles. So what's the analog of a rectangle for triple integrals? It's going to be something called a box. And so we use B to stand for box. And box is basically just a 3D rectangular prism like we have here. And so a box, the bounds are going to look like this. X is going to go from A to B, Y is going to go from C to D, and Z is going to go from R to S. So it's kind of a little tricky to draw here, but I guess this would be D, this would be B, and then this up here would be S, the upper bound for Z. But yeah, anyway, boxes are going to be precisely the regions whose bounds are all numbers when you do a triple integral. And so we'll do the same convention for triple integrals as we did for double, that you're going to keep the inside stuff together, the outside stuff together, except now with triple integral, we also have an inside layer as well. And so just like with rectangles, the order is important. You can freely switch the bounds around as long as you keep which numbers go with which variable consistent. So for example, yeah, you could write it as dz dy dx like I did the first time, or you could write it as dy dx dz like I did the second time. And just make sure you keep the appropriate bounds with the appropriate variables. And it doesn't matter which order you do it in. As far as calculating triple integrals, it's going to be this basically what you expect. So if I pause this here, well, I'm not going to. If you pause this here and you thought about how you would actually calculate it, thinking about what you learned last week as far as double integrals go, I think you'd be able to figure it out. Basically, you're just going to work your way from the inside out, do your partial antiderivatives with respect to the indicated variable, and go on from there. So, okay, let's do one here. Say I have a density of xy plus x squared e to the z, and I want to calculate the mass of a box with this density function. And the box is located at x between 0 and 2, y between 0 and 3, z between 1 and 4. So these bounds are all numbers. It doesn't matter what order we do things in as long as we're careful and keep the appropriate bounds with the appropriate variables. So I'm just going to do this dz dy dx. So as you could see, I've kept the z bounds with the z, I've kept the y with the y, and the x with the x. And so yeah, we're going to do basically one more step from what we were doing last week. And so I'm going to anti-differentiate with respect to z, which means that, well, I pretend x and y are constant. So what's my z antiderivative? Well, xyz plus x squared e to the z. And that's my inner step. I don't do anything with the x or the y integration that occurs outside of that. And I think I screwed up these. There we go. So yeah, do your anti-z partial z anti-partial derivative. Z partial antiderivative. Sorry. Anyway, and then you plug in and subtract. So I'll get 4xy minus xy, so 3xy, and then x squared times e to the fourth minus e to the 1, which is just e. So whatever, you plug in and subtract. And then notice, after we've done that innermost layer of z integration, we're left with a double integral. So at this stage, it's exactly what you did last week. So now it's just like double integrals. So my y antiderivative is 3xy squared over 2 plus x squared y times e to the fourth minus e. And I plug that between y equals 0 and y equals 3. And from there on, I'm not going to finish this. You guys should on your own. But it's just like what we were doing last week. So as far as triple integrals go, setting up for a box is easy. And calculating once set up, and by set up, I mean, bounds for iterated integral. So once you have it set up, you got your bounds all ready to go, you've decided on an order, all that fun stuff. Calculating once it's set up is just work inside out, using the same exact types of ideas you did for double integrals last week. Okay, and so what we're going to spend the remainder of today as well as tomorrow doing is talking about the situation when you're not dealing with the box. Unfortunately, it's going to be more complicated, just like the situation for non-rectangles was more complicated for double integrals. So if your region's not a box, you're going to have variables somewhere. And so the same number one most important rule from last week applies as far as where are variables allowed to be, which variables are allowed to be in different places. Well, it turns out that as long as your answer spits out a number, you're fine. And so again, by number, I don't mean vector versus scalar, I mean function versus constant. So number means it's a constant. It's not a function of x, y, or z. So if you think about it for a while, it's going to be similar to last time, where with the rules for double integrals, you could think of as, okay, your outermost bounds have to be numbers. Your inner bounds are allowed to have the outer variable. That you practiced enough of those that you saw that, you know, for dy dx, you were allowed to have x's on your inner y bounds. For dx dy, you were allowed to have y's on your inner x bounds. But so anyway, for right now, for today, let's just focus on dz dy dx for our triple integral. And so, okay, I basically know that this is going to have to be the situation for the outermost bounds. That because if you rewind back a couple slides, you see that what happened after I did the innermost step, I was just left with a double integral. So basically all the rules that we figured out last week for double integrals, that's still going to have to be going on for the bounds on the outside of our triple integral. And then as far as what can happen on the innermost, essentially anything goes as far as, you know, we're only allowed to have x's and y's once we've done the z steps. So it turns out that you can't have z's here. If you did, you're plugging them in, then they would hang out in the end. And so anyway, this is what you're going to want to get used to as far as an allowable triple integral setup. That for dz dy dx, your x bounds have to be numbers, your y bounds can have x, and your z bounds can have x and or y. Is sort of the most general situation that we're allowed. And if you think about it, actually it's a lot trickier. There's actually 6 orders we could do triple integrals in, right? What's the number of permutations on 3 things? It's 3 times 2 times 1. So the general rule then to get rid of the labels x, y, and z is that the outer bounds got to be numbers. The middle bounds can have the outer variable, and the inner bounds can have the outer or middle variable. So let's just do an example. Let's say you're skeptical as to how this works out. Let's just take a look and see that this, in fact, is okay. So let's make sure that this integral that I've set up here spits out a number. So what's the first step? Well, z antiderivative is z squared over 2. I plug in z equals 0 and z equals 1 minus x minus y. So I plug in and subtract my z bounds. So I get 1 minus x minus y squared over 2 dy dx. So at this stage, I guess hopefully you should be convinced that this is an xy double integral. I'm allowed to have x's on the inner y bounds. This will give me a number. But anyway, let's keep going. So if you want to, you can square this out. But I think the easier way to do this is to think about doing a substitution here. So if you do like u is 1 minus x minus y, then du is minus dy, of course. So this is basically going to be 0 to 1 minus 1 minus x minus y cubed over 6 between y equals 0 and y equals 1 minus x. Yeah. If I use the chain rule, take the y partial derivative, I end up getting that exactly. So at this stage, it's just sort of a boring Calc 1 example. So if y is 1 minus x, then I get 0 actually in that numerator. But if y is 0 and it's in the lower limits, the minuses cancel. I think I get 1 minus x cubed over 6 dx. And so again, if you want to spend a lot of time expanding that expression out, you can do that, but I think it's better to do so this substitution goes there. If I do the substitution u equals 1 minus x, du is minus dx, I'm going to get minus 1 minus x to the 4th over 24 from 0 to 1. So I end up getting 1 24th. Okay. So yeah, it's okay to have x's and y's on your innermost bounds. So essentially it's just one more scaled up idea. So this was okay for double integrals, remember? Now we just have a third thing on the inside, and you're allowed to have x's and or y's in your inner z bounds for this type of thing. Okay. So this is where I usually ask, okay, who's really freaked out by all these variables there? What on earth do these bounds mean? That's what we're going to start talking about now. So in the same way as for double integrals for dy dx, it was about top and bottom curves. What you're going to want to do is think of doing a triple integral, getting the bounds set up in a two-step process. And so the first step is to worrying about your innermost bounds first. So that's our first step to understanding what's going on with the triple integral. So what is this u1 of xy and u2 of xy? Well, it tells me that my solid region E lives between the surfaces z equals u1 of xy and z equals u2 of xy. So remember, the graph of u1 of xy and u2 of xy, the graphs of those functions are surfaces in R3. And the lower z-bound is your lower surface. The upper z-bound is your upper surface. So we have our upper surface, or I'll just call it top surface, and bottom surface. Okay, that's the first step, figuring out what's going on with your surfaces. And then, okay, what's going on with the x and y bounds is you just do what you did for double integrals for this shadow. So we're going to call D the projection or shadow of E into the xy plane. So here's unfortunately, I couldn't find an example where these were for the same thing in the book, so this doesn't exactly line up. But hopefully you get the idea that you have your solid region, you have your shadow. You have your solid region, you have your shadow, and then the shadow is just something in the xy plane. So as far as the dy dx bounds go, just do that the way you did last week. So that's what the g1 of x to g2 of x are for your outer x and y bounds. Okay. And so then the question we want to answer right now is what region were we dealing with a few minutes ago for that example? So for what region E is this iterated integral the triple integral of z on this region E? Okay, so the innermost z-bounds are telling us the bottom and top surfaces. So let's draw that. Z equals 0 is the bottom surface. Z equals 1 minus x minus y is the top surface. And so the top surface looks like it's a plane. So z equals 1 minus x minus y. Hopefully you recognize that you could rewrite that as x plus y plus z equals 1, which is a plane. And I'll show you the general shortcut in a second. The plane x plus y plus z equals 1, if you want to sketch that, it has x-intercept 1, 0, 0. It has y-intercept 0, 1, 0. And it has z-intercept 0, 0, 1. So this top surface is the plane x plus y plus z equals 1. So you want to think of, yeah, we're starting at the xy plane and we're stopping at this diagonal plane. And then it's telling us that the shadow, this orange region here, that's what's going on with the dy dx. So you could draw that first if you want. It doesn't really matter which order you go in. It's telling me that the shadow of what I'm dealing with, y equals 1 minus x, is the top curve. And y equals 0 is the bottom curve. This intersection happens at x equals 1. But this orange region, the shadow of E into the xy plane, is this triangle here. And so for what region E are we dealing with? I would say, well, it's the solid tetrahedron with vertices 0, 0, 0, 1, 0, 0, 0, 1, 0, and 0, 0, 1. So tetrahedron's just a fancy way of saying it's a figure with 4 triangular faces. So it's kind of like a pyramid, but a pyramid usually has a square base. So a pyramid, I guess, would say what? It's got 1 quadrilateral and 4 triangles as its sides, but a tetrahedron just has 4 triangular faces. And that's what we're dealing with here. That our bottom surface was z equals 0, our top surface was that x plus y plus z equals 1, and then the shadow was that triangle, x goes from 0 to 1, y goes from 0 to 1 minus x. So if this double integral stuff doesn't seem completely natural for you right now, go back to last Monday's lecture on 15.2 and make sure you're completely comfortable with double integral general regions. Because first of all, that's a subset that shows up in our shadow for these triple integrals. But also it's the triple integral, the whole idea is just a scaled up, more complicated version of that. So if this XY bounds orange region picture here is mysterious, review last week's stuff before coming back to this. And I guess I should show you this shortcut real quick for sketching a plane. So the plane x over a plus y over b plus z over c equals 1. It has points, I mean, it's pretty obvious when you think about it, but this could just quickly help you either come up with the equation or sketch the plane. I think, yeah, I guess one of the homework assignments, one of the homework problems from section 12.5, when we did that a while ago for you 230 people, for your 232 people, hopefully when you were in 231, you did this kind of thing. But if I want to sketch this plane with that equation, I can, it's easiest to draw if A, B, and C are all positive. This wouldn't make sense if either of them, any of them are 0, but essentially you can sketch the first octant piece of this plane, assuming A, B, and C are all positive, as going to look something like this. So this would be the picture if A, B, C are all positive. So anyway, that's the idea with triple integrals. The innermost bounds are your top and bottom surfaces, and then the outer two bounds are the double integral bounds for your shadow in the XY plane. So tomorrow we'll do lots more practice with this stuff, and then I'll show you how you basically can rotate this picture and have either dy or dx on the inside, depending on what's convenient. But yeah, we'll pick up there tomorrow, and I will see you then.